Let's take a look at comparing linear and exponential functions. So let's review. Linear functions are in the form of y equals mx plus b. They look like a straight line that has a slope and a y-intercept typically. And then exponential functions look like they rise quickly or they are falling quickly. So like there's a dramatic change in how quickly they're increasing or decreasing. So you can use patterns between consecutive data pairs to determine which type of function models the data best. Linear functions have the differences of consecutive y values that are constant, where exponential functions have consecutive y values that have a common ratio between them. But in each case, the differences of consecutive x values need to be constant. So let's take a look at some examples of is it linear, exponential, or neither, and why. So in this first graph, I can see that this looks like a straight line that has a constant rate of decrease. Like it looks like it's definitely going down by the same amount each time, and that is a consistent, like the difference between these y values is going to be the same. So I would definitely choose linear for this first one. And let's put that the graph is a line that shows a constant rate of decrease. Okay. Let's look at number 2. So number 2 gives us the values for a tennis tournament, and it's rounds 1, 2, 3, 4, and 5. So we can tell by the table that the x values are just going up by 1 each time, which is important because either linear or exponential, that's what it was saying at the top of your paper, the x values, like the difference between them needs to be constant or you can't really compare at that point. So these are all going up by 1. Then we look at the y values. So 64, if we had to go to 32, we could either subtract 32 to get there, or we could say 64 divided by 2 would also end up as 32. So it's like you're taking half of 64. So let me write that. So it's like dividing by 2. So let's see what happens on the next one. So it looks like 32 goes to 16. So then I'd have to subtract 16 to go from 32 down to 16. But if I divide 32 by 2, I would also get 16. So now we can take away the fact that subtracting was an option because they'd have to have the same amount. And now we're looking at, do they all have a common ratio of 1/2 or divide by 2? Here, let's put both. So we could say 64 times 1/2 equals 32. That worked. 32 times 1/2 was equal to 16. So that also made sense. Is 16 times 1/2 equal to 8? And yes, it is. And then is 8 times 1/2 also going to give us 4? So yes. So this has a common ratio for the consecutive y values. So let's write that over here. So it definitely looks like this one is exponential for that reason. So y, we would say the consecutive, so between each y value, consecutive y values have a common ratio of 1/2. Okay, so let's look at number 3. We have y equals 4x. So if we go back and look at our linear form compared to our exponential form, then this might help with this one since they gave us an equation. So I'm going to bring that down here. So we can either say this is in the form of y equals mx plus b, which is linear, or y equals a times b to the x, which would be exponential. But I see that x is not in the exponent with the 4. It's right beside the 4. So I could say that's the same thing as 4x plus 0, for example. And then that would definitely look more like linear form, not exponential form. So let's go with linear because we could say y equals 4x is in slope intercept form. Because it has a slope that's equal to 4 and a b value or y-intercept that equals 0. So it's in linear form. So let's say y equals 4x is in slope-intercept form because it has a slope of 4 and b equals 0. Let's say which is linear, not exponential. Okay, so that's just a few examples of how to determine from a graph, a table, or an equation, is it linear or exponential or neither.